Welcome back. Today we're going to start talking about exploring exponential models. And just to emphasize, in terms of things that we're looking for to begin with, we're going to kind of classify it into two groups, exponential growth and exponential decay. You're going to hear those terms are used over and over again. And eventually you're going to get to the point where you're able to sketch the graph of an exponential function. Yes, once again, there is Math Excel for you to play with this evening. But let's get started with a little bit of vocabulary because, let's face it, you guys have never really seen something having to do with exponential models. So let's get rolling on this. Okay, first off in our vocabulary, an exponential function will always be some form of this setup here. What we've got is we've got a constant out front. We've got the base of the exponent, and the thing that makes it an exponential function is going to be that x is not in the regular expression. It is the exponent here. And that's really the big key thing that you need to be looking for on that, is find where the exponent is. Now we call b the base. It's the base of an exponent, and that can change depending upon the problem, but it's definitely going to be something that you guys are going to be changing with. We also have an exponent x. That's our independent variable that varies throughout the problem. Now, for exponential growth problems, you'll notice that we are increasing. And when you hear the term something is increasing exponentially, that's usually something bad, like, I don't know, the amount of pollution on the planet, or the amount of people, or the amount of animals, depending upon a certain situation. It will grow exponentially. The amount of garbage that has been produced, things like that are, common phrases that I've heard used. On the other hand, there is a thing called exponential decay. Now, if you've ever heard of radioactive decay, this is an exponential thing. How it breaks down, what happens. The key thing that I want to emphasize as I'm talking about this, though, is that in both these cases, we know that the x-axis is going to be an asymptote. Now, what is an asymptote? An asymptote is something that is approached but never quite touched, okay? You always want to get as close as you possibly can. But just to emphasize again, with exponential growth, as your x values are going up, so are your y values. And they're not just going up, they're going up, and the rate at which they're going up is increasing. On the other hand, when we are doing exponential decay, as our x values are increasing, our y values are decreasing, but the rate at which they are decreasing is actually decreasing also. It's not staying at a constant slope. And that's the thing that's really different about exponential functions, is you don't have that constant slope that we really like and are very comfortable with. Okay, so let's keep moving on this. And what I need to do is talk about how do you differentiate exponential growth versus exponential decay when all you have is an equation? Well, the first thing you do is you're looking at that expression. Y equals a times b to the x. You know it's going to be growth because b is going to be greater than 1. Greater than 1. Okay? And then when it's exponential decay, and this is the thing that's going to throw people a little bit, b is going to be in between 0 and 1. In between 0 and 1. So let's kind of take these, two for instance cases straight away. What are some possible values of b? 2, 3, 4.5, 5.75, 11 thirds. These are all values where my b value is bigger than 1. On the other hand, in exponential decay, I'm looking for something that's maybe a decimal, like 0.75, 0.25, or 3/5. Any of those things would work, as exponential decays. So here's another example. Now notice, I have that a value. What the value of a is not terribly important here. Um, you're just focused on what the b value is. Since my b value is bigger than 1, I'm going to say it's exponential growth. On the same time, I look at this one and I'm going to say, well, once again, I really don't care about the A, but in terms of figuring out if it's growth or decay, since 0.95 is less than 1, well, we can say it's going to have to be an exponential decay function. Okay, so anyway, let's see what we want to take a crack at next. Okay, identifying something whether or not it's growth or decay. Now this should be something that you can fairly easily take a look-see and see what we've got here. Okay, just look at it, give yourself a second here, pause. You might want to even jot down your answer on this. Okay, and I'm going to continue now. And I'm going to say, well, I need to look at my b value. In this case, my b value is clearly going to be bigger than 1, because if it was just 1, it would be 10 tenths. This is 17 tenths, so I'm going to say it's exponential growth. Now, the next thing is finding the y-intercept. Now, finding the y-intercept is actually very, very easy because we remember one of the rules that we had. Remember that any number to the 0 power was 1. Well, guess what? If I'm looking for a y-intercept, that means I am looking for what happens here when this is 0. Well, if you take this value and you raise it to the 0 power, that just became 1. So guess what? I am now looking at a value of 0, 12. Okay. Next, change gears real quickly. I look at this one. I say, ooh, that b value is less than 1, so I'm going to say that this one is decay. And once again, I look at this and I'm going to say, well, if I place a 0 there, that means that this whole thing becomes 1. So therefore, I'm just looking at 0, 4. Now, at this point, I'm truly hoping that people are saying, well, wait a second. What that means is if we've got a growth or decay, all I really need to do to find my y-intercept is say 0, comma, the a value, or the coefficient out front. And I'd say, oh, you're so smart. Anyway, moving on. Next, we're going to take a look at this one. The only thing that's a little bit off on this is, well, where's my a value? I have that implied a value. It's not there, but we all understand that it's 1. So I'm going to say, well, my base this time is bigger than 1. It's 6. So I'm going to say it's exponential growth. And my a value is 1. So I'm going to say that this is just going to be 0, 1 there. Okay? And we could do all kinds of stuff and more examples here, but I'm going to keep it short and sweet. I'm going to say, well, if I was just going to do this quickly, I'd say this is decay, this is growth, and this is growth. And I'm going to say 0, 2, 0, 129, and 0, 1, 100 to find my y-intercepts. See what I mean? Quick, easy, and relatively painless. Okay, well, let's see what we've got here. Next, we've got this sort of expression. Okay, when people talk about things compounding, somehow, that is an exponential thing. And that is why people with money tend to get more money because, well, money grows exponentially, which is why families with money tend to, well, have children with money. And it's, one of the things that we can talk about inequities in America, but that's one of the things that is definitely there. So what we need to do is we need to say, well, my a value is going to be, as you said, your y-intercept. It's also my initial value. So I'm going to call that an initial value. There you go. And it's going into a college savings account for 4 years. The account is going to pay 6% interest annually. So if I was going to turn this into an equation, I would say the amount of money in my interest-bearing account. Now, technically, I could do y and x, but it's not interesting to do it that way. Let's say I've got $2,000 to start with, and it is going to pay 6% annually. So this is when I've got, those are the number of years. And I'm going to rewrite this very carefully to make sure that everybody's clear on this. I do not write it as 0.06. The reason why is that would be a fraction of 2000. I need to make it so it grows. I need to make it bigger, or otherwise nobody would ever invest money. Now, since I've now written it as a number that is bigger than 1, I know that it's going to be exponential growth, and I also know that my initial value is going to be 2000. Okay, give yourself a second, please, and see if you can come up with what the initial value is, or what the y-intercept is, and whether it's growth or decay. Okay, and we're back, and let's take a look at this. Well, it's pretty easy to see that this is my initial value, okay, my y-intercept, if you will. So I'm going to start off with 30,000. And next, we're talking about something per year, so it's going to be based off of the number of years. But here's another magic business word: depreciates. Okay? Now, the root of that word is going to be something that should be highlighting to you that it's going down. So, what I'm going to be looking at is, I know that the amount of money that I'm getting, or the amount of money I'm going to get out if I sell it after 5 years, is going to be less. So, how do I express that? Well, what I'm going to do is I'm going to say this. I'm going to say that I've got 100%, and I'm going to subtract 17% per year. Okay? Hopefully people are not getting too lost on that, but we're going to say that that ends up getting me 0.83, or 83%, and that's 0.83. Now, again, I'm going further than you really need to do, but I would say that the key thing you need to do is recognize in this word, depreciates means it's going down, so this is going to be decay. Much in the same way that I'm investing money up in this, and you're not going to want to put money into something that you're losing, so this had better be growth. Okay, people still good, I'm hoping? If not, feel free to ask me questions about this the next day in class. Next, let's take a look at an actual graph. Okay, you are asked to sketch a graph of an exponential function by hand, identify the y-intercept, the asymptote, the domain, and the range. Okay, do me a favor and copy this down. Go ahead and freeze the video so you can get caught up, and I will get you someplace. All right, so let's do the easy ones. For example, when I substitute 0 into my equation, that means this is 0. So I'm going to be looking at 2 to the 0 power, which is 1. So I'm looking at 3. Okay, that's relatively easy. And then the next one I'm going to take a crack at is going to be the value 1. And I can substitute 1 up in here. So that's going to be 3 times 2 to the first. Well, 2 to the first is 2. 3 times 2 gets me 6. And we're plenty happy there. The one that might cause people a little more stress is trying to substitute in -1. That's going to be 3 times 2 to the negative first. Now, if you remember your properties, you might remember that if I've got something to a negative power, that's going to be the same thing as 1 over that thing to that negative power. So all I need to do is say that this is just going to be 3 times 1 over 2, or just plain 3 halves. Okay, so those are the 3 points that I've got to kind of play with as starters, and let's see what we can do about coming up with a sketch of a graph based off of just those 3. I'm looking at 0, 3, got it, 1, 6 up here, and then I've got -1, 3 halves, which is there. Now, again, my y-intercept I'm hoping is very easy. You're going to say 0, 3. Okay. The domain is going to be, well, It's not going to stop ever. So exponential growth and exponential decay will always have a domain from negative infinity to positive infinity. Again, negative infinity to positive infinity. Now, what we're looking at as we go to the right, what is going to end up happening? You might notice that what I'm doing as I go from here to there is I divided by 2. Here to there, I'm going to divide by 2. Anybody want to hazard a guess? Yeah, I'm going to divide by 2 to get to my next point, which is going to be over here. And then I divide by 2 again, divide by 2 again. And I can keep dividing this by 2 until I get an infinitely small thing. So in fact, I am going to have a graph that looks like this. Now, I'm going to say that that is going to be my expression. But I also have something that's called an asymptote. I'm going to draw that in. It's a dotted line. Do not draw it as a solid line. It always must be described as a dotted line. So that asymptote is a number that you approach but never quite get to. I can keep dividing 3 by 2 forever and ever and ever and ever. Is it ever going to be 0? No, it's not. So what we say is my asymptote, that borderline that I'm not going to go to, is going to be y equals 0. And finally, I'm going to take a look at my range on this, and I'm going to say, well, what does my values of y go from and to? Well, they go from 0 up to infinity, but notice, again, it never quite gets to 0, so I'm going to use the parenthesis here, just like that. Okay, give people a couple seconds. You can stop this video to try and get caught up. All right, then let's take a look at this one. Same sort of thing going on. I'm going to try and fill in some values. Again, 1/4 to 0 is still going to be 1, so I'm going to say I'm looking at 2 here. And I'm going to say, well, when I raise, when x is 1, I'm going to be looking at 2 times 1/4. Well, 2 times 1/4 is 2/4, which reduces to just be 1/2. So this is 1/2 here. Okay. Still not that difficult. All right. And let's see what I can do. Oh, wait, I want to go back up here for a second. Let me briefly mention, did anybody notice that here my base is bigger than 1, and so it's getting bigger, it's growing. Here my base is in between 0 and 1, so I'm expecting this to get smaller as I go from left to right. Well, let's see if that actually pans out here. And let's see what we've got going on. I've now got 2 times 1/4 to the negative first. Well, let's see. It's going to be apply the negative exponent to both of these, which means I'm going to end up with 2 times 4/1, which gets me 8. Okay, and that is going to get me something. All right, now, real briefly, I can quickly sketch this graph and see what I've got to play with here. I'm looking at -1, 8, which is way up here. I've got 0, 2, which is down there, and I've got 1, 1/2 here. Now, what's happening as I progress from left to right is I'm dividing by 4, I'm dividing by 4, and no surprise there, the next one's probably also going to be dividing by 4. So you can see what's going on with that. Okay, and what's happening is once again, it's going to get closer and closer to my asymptote, which is once again going to be x equals 0. Good so far. Now, what happens is my graph comes in and I'm going to draw something like this. Okay, but I want to make sure I've sketched that asymptote, so I'm going to use a dotted line there so that everybody understands that that's what I'm approaching. Okay, let's briefly touch on a couple other things, like my y-intercept is at 0, 2. My domain is negative infinity, positive infinity again. The lowest y value is going to be 0, and it goes up to infinity. Okay, not too bad. All right, Let's see what we've got going on then. So, in general, what would I say are the things that you should kind of keep in mind by seeing this? Well, there's some basic characteristics of any exponential function. First off, your y-intercept is always going to be 0, comma a. Always 0, comma a. For your basic exponential functions, until we start moving them around, we'll start off with an asymptote at y equals 0. And then we can talk about how my domain for all of these is going to be negative infinity to positive infinity, and my range is just going to be from 0 to infinity there. Okay? Major questions? I hope not. So the next thing I'm going to have you guys do is see if you can come up with a sketch on your own of an exponential function. So take this, see if you can sketch it on your own, and see where things get to. Okay, since I'm not in person, I really can't check it, but I'll run through what sort of answers you should get. So when I plug 0 in there, I'm going to be looking at 4. When I plug 1 in there, I'm looking at 2. And when I plug negative 1 in there, I'm going to come out with a value of 8. Oops. There we go. So as I go from right to left, not surprisingly, I'm dividing by 2 and dividing by 2, which, again, that's what that means. So I'm not surprised that I'm dividing by 2. Let me go ahead and sketch my points. Negative 1, 8. Okay. That looks an awful lot like what we had last time, though. It's a little bit different. So negative 1, 8 is right up here. 0, 4, right down there. And 1, 2 is there. And since we're having these, I could even draw in another one, and draw in another one, and draw in another one. But I'm also going to draw in my asymptote at y equals 0. I can kind of connect the dots so it looks like a pretty curve. All right. And then I can fill in some values. My y-intercept is still 0, 4. My asymptote is y equals 0. My domain, negative infinity, positive infinity, and my range is 0 to infinity. And we could take the time to try and continue on this, but it's really not that exciting. And my guess is you guys are okay on that. If not, please feel free to ask me about this next time we're in class. Now, let's hit you guys with one last one here. Which one of these functions does this graph represent? Okay, give you guys a couple seconds. Going once, going twice, and here we go. Okay, so the first thing I'm going to do is let's see if we can identify our A and our B. And well, that's kind of my standard form. And the first thing I'm going to do is I'm going to shoot for my A, and I'm going to say my A is going to be located right there. And I can say that one fails. So does that one. How come? Because I'm looking at a value of 2. So done. Got my answer there. Okay, we will build on this next time. Look forward to seeing you then. Have yourselves a lovely afternoon. We could kind of do a little bit more, and I'm going to keep it very, very brief on this. You can keep building on these and keep getting to other places. But just take a look at this one example problem. Is this going to be growth or decay based off of this equation? Just off the equation. Again, I would emphasize, please look at your B value. Since that is less than 1, I'm going to say it's decay. And determine where the y-intercept means. Well, there's my y-intercept, so it's going to be 0, 2.28. And again, reading from the context of the phone, I'm going to say that it's going to be the number of payphones in 1999. Okay, number of payphones in 1999.